Alright guys, today we're going to talk a little bit about capacitors and diodes. We won't touch too much on inductors right now, and I'm not going to get into the physics behind them. I'm not going to get into anything, any of the math behind it. What you're going to do is you're going to look at these capacitors from a very practical point of view, same with the diodes. And maybe as we go on, I'll touch more on their physical and sometimes chemical properties. But right now we're just going to look at capacitors and what they do. Some parts of this you might not understand, but I think you'll get a basic idea, and as you go along, as with everything electronics, if you do your own experimenting, you really learn exponentially. So first of all, let's look at capacitor. I need a couple different schematics for capacitor. This is a non-electrolytic capacitor, which means there's no polarization. Doesn't matter if the signal's coming from here or in the negative, there's no positive or negative. You can hook it in a circuit either way. Here is an electrolytic or a polarized capacitor. Means that if I was to put it in a circuit, if I was to say put it in a circuit like this, I would have to put it in so the positive is facing the positive line of the voltage. If I put it in backwards, I could damage the capacitor or even blow it up, depending on how much power there is at the power supply. Not a good idea. Always make sure you put it in the right way. So many different uses for a capacitor. So let's talk about some of the simpler ones. Okay, so say we've got a big microphone here. This circuit we'll get into much later in the videos, but when we want to isolate a sound wave or an AC wave. Now, maybe before I start with this explanation, I should characterize DC and AC. DC means direct current. Direct current basically means is 0 volts down here, let's say 10 volts here. Straight voltage, straight 10 volts, or straight 5 volts. No waves, just battery power or power supply power. There's often a little bit of noise on the top, and by noise I just mean interference, static. Noise is a bunch of different things. It's always there. But anyway, AC is what you get in your wall socket. AC, you get positive and negative voltage. You got 0 volts, negative voltage, positive voltage. This is your amplitude. This is your negative amplitude. This is your peak-to-peak value. This is your peak value, voltage value. Anyway, so here is when you plug something into a wall, the wall socket works at 120 volts at 60 hertz. And what 60 hertz means is that you get a positive revolution and a negative revolution 60 times in 1 second. So realistically, if you look in if you're in your room, you're looking at the lights. If you ever see a light kind of flickering, it's not really flickering. What it is just basically turning on and off 60 times a second. And never go near your wall socket because that's bad news. You don't ever want to touch that. The wall socket can provide tons of current and can kill you. Anyway, so when we'll actually get back to this. This is a good example because we can use this for many different examples using capacitors. Capacitors, if I have DC here, I will get nothing here. Capacitors will not pass DC, but capacitors will pass AC. So just another look at AC. What a hertz is a cycle. This is 1 cycle. Positive to negative positive to 0, or 0 to positive to 0 to negative to 0. That is, if this happens once in 1 second, that's 1 hertz. So if I do this 60 times, and that counts for 1 second. 60 times in 1 second, that is 60 hertz, 60 cycles. 380 degrees. 380 degrees, 60 times in 1 second. In communications, we use megahertz and gigahertz, which means those cycles happen millions in millions of times per second. So it's hard to fathom, but what we're going to get here, if someone's speaking into this microphone, we're going to get our DC line, say 5 volts, but we're going to get our audio signal, which has an AC component to it, which you can see little squiggles. That's our AC component. So what we're going to see here, what we're going to see right here, is our DC component, which from the 5 volt line, and our AC component, which is the audio signal that's vibrating, being created from the microphone. But what we're going to see here is we're going to see just the AC component created from it. So, and that's great because we can amplify that signal and get a beautiful AC signal from that using certain amplifiers, which of course we'll get into later. But that's one of the reasons why we use capacitors. We also use capacitors for filtering. Now, knowing that capacitors can pass AC and not DC, say we've got an input, and we'll get into filters later, but this is what's called a high-pass filter. Signal in, signal out. Using this a formula, which we're not going to get into because we're not going to touch on filters today, we can basically pass certain frequencies and block out other frequencies. Low frequencies won't pass here, but once we get to a certain calculation based on that resistor and that capacitor, we can pass certain signals. Filters will be left for another day. We're not going to worry about them, but that's another reason for we use capacitors. When we make an AC to DC power supply, you notice you plug in wall transformers. Let's say we've got our AC plug, our 120 volt plug. We need what's called a power supply, which we'll touch on later, which basically what it does is it takes 120 volts at 60 hertz AC, changes it into a lower, more acceptable voltage, something that we can use in DC. We can change AC to DC, so we can use it for your clock radio to power the DC circuits in your clock radio. So what essentially it does is we use what's called a transformer. Transformer steps down the voltage, makes a big voltage, a little voltage. It's still AC. We use diodes, which we'll get into later, and the diodes are able to rectify the signal into just a positive wave. So turning an AC wave into a DC wave, and then when we feed that signal through a capacitor, if we feed this signal through a capacitor, what it does is, dang it, if we put a capacitor in parallel with ground, it acts to charge on the positive plate. It'll hold the charge on the positive plate as it'll charge and discharge and charge and discharge. A capacitor can, as I'm saying here, can be used basically as a battery, a very temporary battery, but it can be used as a battery. So you see that we're getting positive. If we're looking at a power supply after it's being rectified, we're still getting some bumps here. We don't want to use that. We want a nice straight, or as straight as we can get it, DC supply. So what that capacitor does is changes that to, because it charges and discharges and charges and discharges. So that's all stuff we can get into later, but these are I'm just trying to go over with you certain reasons why you'd use a capacitor. Now, another thing we could do is we use what's called a decoupling capacitor. So Not very often. Let's just say a battery. We don't have to use it with a battery, but say we've got a wall transformer, so a wall power supply. You know those big bulky things you plug into the wall that plugs into your stuff? You know, you plug that into the wall, and that does all your power supply stuff for you. But when you plug it into your circuit, say I wanted to plug this into a 7805. Now remember what 7805 is. Say we got 9 volts DC here because of that wall transformer that's doing the power, making the power supply for us. We're still going to have we can't rely on this thing not to give us a whole bunch of noise. We're going to get a DC, but we're going to have an AC component with it. So what we're going to do is we're going to take capacitors, very small ones, with very small values, and connect the input and output through the capacitor to ground. It basically acts as a filter. It filters out all that extra noise. Not all of it. Noise is never eliminated, but filters out a lot of it. So it just makes this 5-volt signal a lot cleaner. Now, capacitors, something like this would be 0.1 microfarads. And I haven't gotten there yet. Capacitors are measured, their values, they're often given 2 values. They're measured in farads, the higher the values in say 1 microfarad or 10 microfarads or 100 microfarads, the higher farad value, the better. The higher the value in farads, or rather microfarads or millifarads, that's very high. You'll never see a capacitor like 1 farad capacitor. That's huge. But the higher the value, the better the capacitor's ability is to charge current, to hold and maintain current. So, but it's also given a voltage level. So you don't want to put sorry, running out of room here. You don't want to put a battery supply with 100 volts DC and put a capacitor in parallel with it that can only handle 50 volts. Because if you do that, what's going to happen is, boom, it's going to short it out. Now what a capacitor is, basically 2 plates. I'll use an electrolytic one, or a polarized one as an example. What this can do, if we're looking at it, a charge-discharge, looking at it like a battery, we know that electrons will collect on here. Will collect on here. Remember, we're looking at this from a practical point of view. I'm not going to get heavily into it because there's actually more. And if any engineer sees me right now, he'd probably smack me across the face. But what I'm trying to tell you is here is say I've got this making my power supply really neat, but I've also got that at what's called an amplifier. It's not an inverter. It's an amplifier. What it'll do is say the power shuts off. It'll keep the power going temporarily afterwards because these electrons, which are being charged over here because of a power supply over here, are still being charged. So even after the power is taken away, there will still be a moment where the circuit will still have a charge to it. And this is a bad example, but if we had a circuit where it wasn't going to discharge, if you disconnect the power supply from a capacitor and you leave it, you can hurt yourself. And what I'll show you is a safety circuit. It's not a safety circuit, but let's say I put a multi-cell battery, 20 volts or 200 volts, and put a whole bunch of capacitors in parallel with it to keep maintain a charge. If this is a stupid example of a circuit. This is a bad example, but I'm going to show you what I mean. Say I want to charge up these capacitors. Remember, all these grounds are connected. I just want to charge up all these capacitors to, let's say, the 200 volt capacitors. So I'm not exceeding the limit, but what's going to happen is as soon as I remove the power from the circuit, all the electrons stored up here at 200 volts are going to stay there. So if I take those, and what this will do is it's not going to supply more than 200 volts, because remember, they're in parallel. Same voltage, twice the current. If I added another one in there, 3 times the current. Now what you got to do is we haven't talked about power yet, but this is, if you're charging 3 of these in parallel, that's 3 times the current of what it would be if we just cut this off. So we have to add what's called a bleeder in there. And what a bleeder is, we won't talk about power, but a very high resistance, very high. Let's say 100K or 1 mega. Oh, 1 mega is 1 million. So that if power is disconnected for some reason, we don't want those, and for some reason we don't want those capacitors to stay charged. We got to bleed it off. It'll bleed off very slowly, but it will bleed off all the electrons stored on the plates. So there's a lot to be said about capacitors. There's a lot for you to retain here, and there's just never enough time. So always be wary. I've been in a situation where I've shot myself very badly with a very small high voltage capacitor. See, you don't have to just worry about the voltage. I mean, if we have a 200 volt, 2700 microfarad capacitor, which is 2.7 millifarads, fully charged, and the circuit does not have a bleeder capacitor or a bleeder resistor on it, and I touch the positive and the negative leads, it's going to, and I'm grounded, it's going to hurt so badly, and I've been there. Anyway, capacitors are nifty. You can do a lot of stuff. A lot of oscillators work with capacitors. Just about every analog circuit you can think of has capacitors, and most digital ones do too, mostly for filtering or for decoupling. But those are capacitors. We'll talk about them more with the circuits we actually use them in the videos. But now let's talk a little bit about diodes. Now diodes are a bit more complicated. We're not going to delve so much into diodes for now. We're going to get into them more as we go along, but they can be used for a bunch of other things. The symbol for a standard diode is this. Now, I'm not even sure if you can see that. It's just triangle with a stick on the end. This is the negative. This is the positive. Anode, cathode. Now, the way you can remember this is, I like to look at the alphabet as the A being the positive end and Z being the negative end. Anode, positive, C's further down the chain toward the negative. That's maybe just the only way I look at it. I always remember it. It's up to you. It might be a corny way of looking at it, but what this basically says is that positive voltage has to be here in order for it to complete the circuit. If I put positive voltage here, nothing's going to be here. It only passes one way. Now, alternatively, we haven't touched on negative voltage, we won't for a little while. If I put negative voltage here and positive here, well, I suppose it's the same thing, but just backwards. Or rather, ground, then it will conduct. So it's a matter of conducting. Oh, geez, there's so much to be said about diodes, but let's show a couple different uses of this circuit. So if I take a DC power and I put a diode. Wow, I'm really awful with that, aren't I? I like music more than I like art, so you'll have to pardon my awful penmanship. I never could draw. You should see my handwriting, it's disgusting. So, one of the interesting things about a diode is they always, when it conducts electricity, you have to have at least 0.7 volts, so 700 millivolts. So there will always be a 700 millivolt drop when it's conducting fully. Now it might be a little bit less, between 500 and 700, but in school they teach you roughly 700 millivolt drop. So we have 10 volts here. We got one resistor, 700 millivolt drop. We're going to have 9.3 volts across the resistor, because there is a drop here. Remember, this is the positive, it's the negative, or the negative. So, what if I did this? What's going to be across R1? Because we've got a positive polarity on the cathode and negative on the anode. It will not. This circuit will not conduct electricity. So let's get rid of this. That's just to show you. Basically, there are tons of different types of diodes for tons of different reasons. We're just going to talk about standard diodes right now. So we'll look at a half-wave rectifier. This is basically a very, very basic way of looking at it. The calculations I'm not going to get into, but I'm going to try to show you the practical way of how these things work. Say we got our wall outlet. Unhappy looking wall outlet. We got our hot, neutral, and ground, earth ground. Completely different. It has to do with AC. We're not going to touch on it. So, let's see. What am I doing? Okay, sorry. No, I had a little bit of a brain fart there. I'm going to do this over again. I'm going to connect our wall outlet to what's called a transformer, which is another thing we'll talk about later. But basically what a transformer does is we use a certain amount of windings at the primary, and we can either step it up or step it down based on how many windings there are at the secondary. If there's less windings at the secondary, this is way too advanced for what I'm trying to teach you in this order. I'm just going to say what we're going to do is we'll have in a normal wall power supply in what you're in, say your microwave. We're going to have 120 volts AC, 60 hertz here. We're going to step it down because there have less windings at the secondary to say 10 volts AC. So we're going to have, let's say, there's so much more to be said about this. I'm just trying to get you to understand. So we put this, we get a much smaller voltage AC here, positive and negative voltage. We put a diode in there. As soon as we put the diode in there, we get this. Because negative won't pass along this point. So this is a half-wave rectifier in its incredible simplicity. I'm just trying to show you the diode stuff, not the transformer, not the wall socket. We're not going to get into that. I'm just trying to show you. And then, of course, like we talked about earlier with the capacitors, put a capacitor in there. We'll get a nice clean, not clean, but DC. So there's three different main kinds of rectifiers. There's half-wave, there's whole wave, there's bridge. Bridge being the most useful, the best. And you get the best output, the straightest output, especially when using a capacitor. Anyway, so that's another way we can use a diode. We can use a diode for a couple things. We can use diodes for tons of things. I'm going to use standard diodes. A very cheap way of regulating current or regulating voltage is let's say say we've got a 5-volt line. 5-volt line, ground line. Say we want to bring in a secondary supply, a 9-volt supply. This is a cheap way of doing it, and teacher would probably smack you for doing it, but just for fun, I'll show you. We always have to make sure that we use the same grounds. Say we use 2 different power supplies, we get a 5-volt and a 9-volt. We have to make sure that both of the supplies are grounded together. Same ground, share the same ground. So we got 9 volts. We got a 5-volt supply. And I want to change this 9 volts into 5 volts. This is a bad example, but connect that in series with the cathode facing the 5-volt line and the anode facing the 9-volt line, and you're going to get 5 volts here. Now, as I said, the physics behind this is a bit skewed. I'm just trying to get you an idea of what's going on and how this works. A Zener diode would be a better way of doing that. What a Zener diode is, has a breakdown, a backwards breakdown. So if I have a 9-volt signal here, and I put a Zener diode in here. Zener diode is cool. It looks cool. It's got cool little waves on its hat. I call it the hat, even though it is the cathode. Let's say this is a 5-volt Zener diode. It means that if anything over 5 volts conducts, then essentially, what happens is it breaks down backwards, and anything over 5 volts gets sunk to ground, or sunk to a resistor, or sunk to a different part of the circuit. And that's just a way of looking at it. Engineers don't slide around and trying to get as practical as I humanly can here. So we'd get plus 5 volts here. So 9 volt or anything over 5 volts, if we're using a 5-volt Zener diode, if we're using a 3.6 Zener diode, we're going to get 3.6 volts here. But don't ever use this substitute this for a 7805, because if you have too much current across this, you don't limit the current across here, you're going to fry your Zener diode. They're very small, they're very fragile. They're nifty though. But diodes are used in receiver circuits, they're in rectifier circuits, they're in limiter circuits, they're in tons of stuff. They're in feedback circuits, they're protector circuits. Here's another cool one. Let's just see here. Okay, this isn't a diode really, but here's it's called the crowbar. No, I'm not going to show you the crowbar circuit. We're going to skip on. Just one question for you here. Standard diode. This is the output. Why? Why is the output? So we got 100 ohms here. What are we going to get at Y? Well, we know that 700 millivolts is going to be dropped wrong here. So 5 minus 700 millivolts is 4.3. So no matter what, if we've got one resistor there, we know it's going to be 4.3 volts. So 4.3 volts, 5 minus 4.3 is 700 millivolts, because at this point there's only 700 millivolts to be dropped along this point. So Y equals 700 millivolts. This isn't plugged in anything. This is just a multimeter. Red probe of a multimeter, black probe of a multimeter. Okay, so what about here? 10 volts. Standard diode. Let's just say 1K and 1K. X, Y. How do we figure this out? First we get our trusty calculators. we know 700 millivolts is going to be dropped across here. So 10 minus 700, 10 minus 0.7 equals 9.3 volts. R1 and R2 both are 1K. So we basically divide that by 2. So we know that 4.65 is dropped across here, and 4.65 is dropped along there. So if we want X, 10 minus 4.65 is 5.35 volts minus 4.65 dropped along here, and we get 0.7 volts equaling 700 millivolts, which is just enough left to be dropped across there. Now, do you see how this works? It's all proportional.